It's a warm morning on the Pacific island of Bikini Atoll. The sun sits below the horizon where its warm glow paints the sky. 3 men sit in a bunker beneath the coral's sand. They look closely at a wall of lights. All but 2 are green.
30 seconds.
The firing party commander, Dr. John C. Clark, watches the dials and lights closely. It wasn't his first time detonating a nuclear weapon. It was his 40th. But this one was different. This bomb, named Castle Bravo, is the first weaponizable thermonuclear device.
15 seconds.
Dead silence fills the room, only broken by the soft whining of the instruments.
5, 4, 3, 2, 1.
The road to this point had started 9 years earlier with the first atomic test ever conducted, Trinity. The Trinity device had a yield of approximately 25,000 tons of TNT. It melted the sand for over 1,000 feet in every direction and was heard over 100 miles away. The Trinity device was constructed like most atomic bombs are, a design termed a plutonium implosion device. But how do these nuclear bombs actually work? To explain this, we're going to have to dive into just a little bit of quantum mechanics. All matter is made up of subatomic particles. Here we see an oxygen atom that is composed of 8 electrons, 8 protons, and 8 neutrons. The protons, having a positive charge, attract the negatively charged electrons to stay around the nucleus, in the same way that 2 oppositely charged magnets are attracted to each other. However, we also know that when 2 positively charged magnets are close to each other, they get thrown apart. So then why is it that the 8 protons that are packed very close together in the nucleus don't all get thrown away from each other? The answer is something physicists call the strong force, or more accurately, the residual nuclear force. See, the protons are held together by this nuclear force, along with the neutrons which act to increase the amount of this force in the nucleus. Now, just as light has a particle, the nuclear force also has one, called a gluon, specifically because they glue the neutrons and protons together. Now, in this oxygen atom, the gluons are easily strong enough to keep the nucleus together. But if we go through larger and larger atoms, the magnetic propulsive force between those protons in the nucleus becomes larger and larger, and eventually we hit a point. Ignoring the weird ones, the first radioactive element is polonium. In polonium, the gluons are just not strong enough to hold the nucleus together. Now, what would you logically expect to happen to this atom then? Well, if the gluons couldn't hold the nucleus together, the atom couldn't exist, right? Wrong! This is quantum mechanics, and quantum mechanics does not follow that kind of logic. See, the polonium atom can exist, but there's a bit of uncertainty. For every unit of time, there's a non-zero chance of the nucleus breaking apart into 2 smaller atoms. So, for example, if we take a normal polonium atom and observe it for, let's say, 200 days, there'd be a 50-50 chance of it decaying into 2 smaller atoms. If we waited another 200 days, it'd be a 75% chance. Another 200 days gives us an 87.5% chance of decay. Just like flipping a coin over and over again. This process is called half-life, defined as the amount of time it would take for half a sample of a radioactive material to decay. And this number can vary wildly. Take bismuth. Remember when I said that polonium was the first radioactive element? Well, I technically lied to you. See, bismuth is also radioactive, but has such a long half-life we did not know it was radioactive until 2003. Specifically, a half-life of 20 quintillion years. That is a 2 followed by 19 zeros, a number so large that if you were to stack 20 quintillion sheets of paper, you would have enough paper to get to Saturn and back. 3 times. While on the other end of the spectrum, we have hydrogen-5, an absolute abomination of a hydrogen atom that instead of having 0 neutrons, has 5. And clocks in with a decay time of 86 yactoseconds, or 86 with 24 zeros before it. For perspective, that is almost the same amount of time it takes light to travel the distance of 1 proton. And a very important result of this is that the shorter the half-life is, the more radioactive the atom is. But why does this matter? An interesting academic curiosity for sure, but what is the importance of all this? Well, when a nucleus of an atom decays, it releases energy. A lot of it, in fact. So if we were to say, let's take some uranium and have it decay, it would release neutrons and high-energy photons. And if these neutrons happen to hit another uranium atom, it can cause that one to decay as well. which would release more, and so on and so forth. Now, normally the atoms are pretty far apart, and if you have a lot of atoms far apart, the chance of a neutron hitting another atom and causing a decay is very low. If the atoms are closer together, however, the chance of them fissioning is higher, with one uranium atom decaying, which releases neutrons that cause more to decay, and so on and so forth until the reaction can go completely out of control. This is known as supercriticality. The idea behind a nuclear bomb is to combine these principles to release a ton of energy very quickly. The way the scientists at Los Alamos did this was a series of explosive lenses that created a perfectly spherical shockwave that compressed a plutonium core. As the plutonium core compressed, the unstable atoms got closer and closer together until a runaway fission reaction went supercritical, and the entire bomb became a ball of plasma and gamma rays. Along with this, there's another design called the uranium gun, which compresses two half spheres of uranium by shooting one into the other. Both have the same effect, and both designs were used in Japan, although the uranium gun type weapon has been phased out by most of the world's powers because of the inefficiency inherent in its design, often only fissioning around 1% of its uranium. Hiroshima was bombed 21 days after the success of the Trinity test, and Nagasaki 2 days later. The human cost of this bomb cannot be understated. Thousands of people died in the most excruciating way possible, death by radiation poisoning, while the lucky ones who survived were burnt so badly that their entire extremities were covered in extremely painful blisters. The human cost haunted many of the scientists who worked to build the atomic bombs, but there was one man who thought the current atomic weapons were not large enough. A man named Edward Teller. Edward Teller was born to a Jewish family in Hungary and eventually moved to the US and became a professor at George Washington University. In 1942, he was invited onto the Manhattan Project by fellow physicist Dr. J. Robert Oppenheimer. During the early stages of the project, physicist Enrico Fermi casually mentioned to Teller that a regular fission bomb could be used to detonate an even larger fusion bomb. This idea fascinated him. He became bored with the regular atomic bomb and started designing what he called the super. The super, also known as a hydrogen bomb or a thermonuclear bomb, tries to make the nuclear reaction more powerful by adding material that can be nuclearly fused. Fusion being when atoms are put under tremendous pressure, their nuclei can combine and create an even heavier element, in the process releasing even greater amounts of energy than the previously mentioned fission. More specifically, it works by having a regular nuclear bomb detonate inside part of a larger structure. This structure, in addition to the fission bomb, also contains a part filled with a fuel that under extreme pressure will undergo nuclear fusion. When the fission stage detonates, it creates a massive amount of X-rays. These X-rays are reflected through the internal structure of the bomb, with enough energy to compress the fusion stage, causing a fusion explosion. This process releases multitudes more energy than just the plain fission bomb. It is important to note that you can theoretically add even more fusion stages after this, as many times as you want, allowing you to create larger and larger bombs, although no bomb using more than 3 total stages has ever been created, because anything beyond 3 stages would be so powerful there'd be no practical use for it as a weapon, except, I don't know, destroying an entire country. The design of these fusion bombs is called the Teller-Ulam design, named after the previously mentioned Teller and the Polish physicist Stanislaw Ulam. During the Manhattan Project, Teller focused on designing hydrogen bombs, much to the annoyance of his colleagues. He had a blackboard in his office that had a list of hypothetical nuclear weapons on it. It had bombs from more reasonable smaller yields, all the way up to one bomb that had a yield of 10 gigatons. A bomb so large that if ever detonated, would lift a large chunk of the Earth's atmosphere into space and would, quote, be powerful enough to set all of New England on fire, or most of California, or all of the UK and Ireland. This gives great perspective on Teller. He was willing to go anywhere with his designs. Now, it is still controversial if he would have actually wanted these built or if it was just an academic curiosity, but it is generally believed that in his mind, if countries had weapons of this power, weapons that could destroy cities or nations in seconds, no one would be crazy enough to start a war. And this belief eventually turned into the doctrine of mutually assured destruction. Eventually, after much controversy, the first nuclear bomb to utilize fusion was tested during Operation Greenhouse. Shot George was a standard implosion-type weapon, except that it had a small amount of deuterium and tritium inserted in its center. This so-called boosted fission weapon didn't have much more power over the standard fission weapon, but it proved that nuclear fusion could be created in a nuclear weapon. After the success of Shot George, the test Ivy Mike was set into motion. This test used the standard Teller-Ulam design, except that instead of a stable fusion fuel, it used cryogenic liquid deuterium, which, to anyone who's worked with liquid hydrogen before, knows it is a pain to handle. It required a 3-story building to keep it cool and weighed 74 tons, with over 10,000 people being brought in to help set up the test. These details made it impractical as a weapon, but as a great way to demonstrate the technology, and whether or not the hydrogen bomb would be feasible would depend on the results of this test. The bomb detonated with a yield of 10.4 megatons, 20 times more powerful than the largest fission weapon. The fireball expanded to a size of 2 miles, completely removing the island of Yaguleb and climbing to 56,000 feet in less than 90 seconds. The final size of the cloud peaked at 25 miles high and 100 miles wide. Pilots took off 1 hour and 30 minutes after the detonation to take samples of the cloud. Piloting modified F-84s, they entered the mushroom cloud and encountered severe conditions including heat, radiation, debris, and extreme winds. The radiation was so bad that their instruments maxed out and command ordered them to head back. Unfortunately, the electromagnetic conditions of the cloud had left their instruments unusable. They spent so long looking for the airfield, by the time they had spotted it, they were already out of fuel. Pilot Robert Hagen performed a dead-stick landing, blowing out a tire but ultimately walking away from the landing alive. Jimmy Robinson's engine also flamed out, but a bit over 3 miles from the runway. He attempted to perform a landing on the water, but the plane bounced, flipped, and began to sink rapidly. It also didn't help that the pilots were given lead-lined vests instead of life jackets. Jimmy Robertson was posthumously awarded with the Distinguished Flying Cross. The samples collected from these flights were sent to Los Alamos for analysis. One interested team of physicists out of Berkeley had the interesting idea that due to the amount of radiation and the characteristics surrounding it, that it might have synthesized new elements. The team was able to use these samples to discover the elements 99 and 100, later to be named Einsteinium and Fermium. After the Ivy Mike test, work began on a new hydrogen bomb, one that was usable as a weapon. Construction began and was accelerated after the Soviet Union tested their own half-megaton boosted fission bomb. The Emergency Capability Program was established with the express goal of creating a weaponizable thermonuclear bomb at the earliest possible date. The bomb was so large it was decided not to test it at the main area of the proving grounds, Eniwetok Atoll, but to instead test it at another atoll, Bikini Atoll. The team deciding the location of the test had figured it'd be acceptable to just not worry about the effects on the local islanders, or really any concern of fallout at all. But that the decision to shoot should be reached with the understanding that no health hazard to the task force units and populated islands of the Pacific or radiation safety conditions conducive to possible adverse criticism will ensue. So with a complete disregard for any concern of fallout, the project charged forward. A spot on the reef halfway between Bokonijin Islet and Nemu Island were chosen as the test site, and a small artificial island was created to hold the bomb and its test equipment. Along with this, an artificial causeway was built that was 3,600 feet long that allowed an experiment that used a vacuum tube to measure high-energy rays. A set of towers with downward-facing mirrors were set up extremely close to the bomb with a set of Rapitronic cameras underground to image the first milliseconds of the explosion. The bomb's parts were then moved from Los Alamos to Bikini Atoll via San Francisco. By late February 1953, the device was assembled and ready to go. The weather was the final consideration in each decision to conduct a test. Never were weather data and forecasts more critically checked and screened by weathermen and non-weathermen alike. For periods of time approaching the length of Noah's cruise, several thousand men waited, some with patience, some without, for a change in the upper winds. When it came to weather for a nuclear test, the aspect that was considered the most important was wind. Weather balloons would be launched daily and the winds aloft measured. Fallout would then be calculated. The Marshall Islands are a very windy place, and for that time of year, the average wind speed is around 15 knots. This means that there's only a handful of days in a month where a nuclear test can be conducted. On March 1st, they had their day. When the weather balloon was launched, the path it traveled was relatively small, and the fallout was predicted to fall close to the site. Fallout from 35,000 feet was predicted to fall 45 miles from the closest inhabited area, while fallout from 20,000 feet was to initially drift east, then go back west once hitting the trade winds, eventually falling right back down on the lagoon. The fact that the weather looked good and the previous high-yield test Ivy Mike produced so little fallout added to the perception of the general safety of the operation. The cloud was calculated to go up to 100,000 feet, so as previously mentioned, any radioactive debris should have gotten thrown up into the upper atmosphere and safely diluted. Well, that was the idea anyway. In the words of the weather officer, with extremely high yields, most of the radioactive debris is carried into the stratosphere, where it is trapped and falls out very slowly, thus undergoing normal processes of decay, mixing, and dispersal. All past sampling operations bear out this conclusion, as do the results of the worldwide Fallout program. So everything was a go, and the bomb was primed and the countdown had begun. It's a warm morning on the Pacific island of Bikini Atoll. Aircraft took off and began circling the area. Ships stood ominously over the water awaiting the event, and a small team sat in a bunker controlling and observing the upcoming events. The bomb detonated with a spectacular ferocity. The cameras meant to film the first milliseconds of the detonation were immediately atomized. The massive amount of high-energy particles, unobstructed by the atmosphere, shot down the high-energy ray experiment and caused a 1 kiloton explosion 2/3 of a mile downrange. That wouldn't be much of a concern, though, because the fireball grew to be 4.5 miles wide. Nearly 10 billion kilograms of coral and sand was doused in radioactive materials, vaporized, and then sucked into the cloud, creating a crater 2,000 feet wide and 250 feet deep. In just 1 minute, the bomb grew to be 47,000 feet high and 7 miles wide, towering over Bikini Atoll. The bomb, which was supposed to have a yield of 6 megatons, had a yield of 15. This was due to an error in calculations, specifically a failure in extrapolating data. Remember back to the bomb's design? Fusion fuel is compressed by high-energy X-rays causing the explosion. The lithium that was used in the fuel was composed of 2 isotopes. 40% was lithium-6 and 60% was lithium-7. It was expected from previous experiments that only the lithium-6 would add to the explosion. The lithium-7 was not predicted to fuse or add to the explosion in any way. What was expected was it would absorb a neutron and then become 2 alpha particles after about a second, meaning by the time it split, the bomb was already here, hot, but far below the temperature for fusion. So the scientists believed that 60% of the fuel in their bomb would produce fusible material way too late to contribute to the explosion. This was an incredible mistake. See, the lithium-7 did behave as it thought it would, to a point. Imagine if we were observing a line on a chalkboard, but half of this line is covered by a curtain. The curtain is our experimental data, and the more experiments we do, the more the curtain moves to the right. The physicist asked, what does the line do over there? There are 2 ways of finding out. You can work very hard to slowly push the curtain to the right, or you can guess where it goes. Here, the physicist decides to create a line where he thinks the line will go. Now, it's completely possible that the line follows what he's predicted, but it's not certain. So when the physicist finally does the experiments and pulls down the curtain, he realizes his mistake. He's extrapolated his data into an untested area. Now, here the results aren't that bad. Nothing was lost by a mistaken line on a chalkboard, unless that line was decay time as a function of neutron energy. If a neutron above 2.7 million electron volts hits the lithium-7, which most were, it wouldn't decay in a second, but instead near instantly become an alpha particle, a neutron, and a tritium nucleus. This extra tritium acted as even more fusion fuel, and severely boosted the reaction, leading to a massively increased yield. It is to be recalled that until 1954, one school of thought held that the high-yield surface detonations would create intense fallout only in the immediate area of the shot, where it would be scattered widely around the world. March 1st, 1954 saw the dismissal of that school. Permanently. In the firing bunker stood the scientists and engineers who monitored the test. When the bomb detonated, they were only able to get information on how it went from the radio. That was until the blast waves hit. After only 20 seconds, the bunker began slowly shaking from side to side, but not like any normal earthquake. It was described as being strangely different. It shook so badly that the men had to sit down to stop themselves from falling. This shaking continued for only a few seconds before stopping, in which the men began to breathe a sigh of relief, until another shock hit of the same type, also only lasting a few seconds. A minute later came the air blast. The wave hit with a deep bang and then shifted to a rumble. The bunker creaked but stayed firm. They didn't know it, but just a few feet outside, wooden buildings had been destroyed by the shockwave. Just seconds after the shockwave hit, water began to pour out of the conduits behind the control panel, and even shot out the lavatory with such force it hit the ceiling. This was unexpected, though, as water effects from the blast were not expected for another 6 minutes. They sat in their bunker waiting for a tsunami to wash over them. They waited 14 minutes and nothing happened. After making sure they were not underwater, the men decided to open the bunker. Opening the door, they felt a strange sense of calm, and then when they looked to the west, they saw a massive white cloud slowly growing over them. After a few minutes, they noticed something ominous. The Geiger counter they had brought out to measure radiation began to click, faster and faster. They were in disbelief. They didn't think it was possible for them to be getting this much fallout this early, but they were. It still was not a dangerous amount of radiation. It was extremely concerning, and was rising. The counter rose, 50 millirem, 100 millirem, 500 millirem. By the time they rushed into the bunker, the radiation was at 1 rem per hour. They radioed command, but they also didn't have an idea on how this was possible. Even once in the bunker, the radiation was still growing. They radioed asking if it would be possible to be picked up by a helicopter, but it was decided that that rescue mission would be getting dangerously close to a suicide mission. They were to wait in the bunker until it was safe. The counter reached 100 millirem inside the blockhouse. For short periods of time safe, they went around the different rooms inside the bunker looking for one that had a lower radiation level. They finally settled on the data room, which only had a reading of 10 millirem per hour. Bringing in army blankets to make the wait more comfortable, they sat in the quiet bunker. After an hour, one of the engineers became curious and decided to measure the radiation level outside. Sticking his hand out the door, the Geiger counter measured 40 Rontgen per hour. We were not exactly a happy bunch as we sat around in that small back room. We'd been forced to turn off the air conditioner because it brought in fallout particles from outside. The entire building soon got hot and sticky. Only a few yards away in the construction camp were steaks we had planned on having breakfast. Instead, we were munching sea rations. By about an hour after the detonation, the command ship had started receiving large amounts of radiation and were ordered to leave the area. As the ship departed, the engineers could hear the ship, but their small handheld radios could not reach them. It was also around this time that their power went out. They were left in a dark, muggy room, alone. The radiation at this point was measured at 20 rem per hour. It was decided that the men would have to be driven a half a mile to the airfield and then airlifted out. The entire area they were to be traversing was doused in radioactive materials. So the men wrapped themselves in bed sheets, cutting holes only for their eyes. As the crew heard the helicopters ahead, they left for the landing mat. Once there, the helicopters picked them up and they were flown to the ship and decontaminated. The engineers were extremely lucky to not have been contaminated by radioactive materials. While they absorbed a decent but relatively safe dose, they did not absorb any of the radioactive material itself, unlike the islanders. 80 miles away sits Rongelap and Rongerik atolls. Many of those who lived there were relocated from Bikini Atoll after nuclear testing was initiated 8 years earlier. They knew not of what the Americans were doing. Quote, "The Americans wanted to use Bikini for something that could help the Americans and the rest of the world's nations. The Marshallese thought the Americans would use Bikini for a short period of time." So the islanders continued their lives, hoping that one day they'd be able to return to their home. When the bomb was tested, it created a flash that was brighter than the sun. Lejona Kielinen recounts her experiences. "My old man and I were asleep at the time, but we were surprised when suddenly it was like daytime because it was very bright, even through our eyelids. We woke up immediately. I woke up because, well, I'm not kidding you, because my dream. I did not know what a bomb was like, and what it was used for. I had never heard of one before. But in my dream, I dreamt of the bomb falling from the sky and bursting into flames while I was standing in the middle of the flames, and I was crying and shouting names, but I did not see anyone. I was crying when I woke up because of the bright explosion. I was very, very scared. And then I started to cry again and ran out the door. And I looked for a long time crying. Moments after that, I heard the explosion. It was very loud. It tore my eardrums. After the test and after the shockwave, it was very quiet. No wind at all. Very, very quiet. It was a little after this point that a white snow-like material began to fall on the islanders. It was silverish color, insoluble in water, and under a microscope looked like small crystals. The islanders had no idea what the material was, so they took no precautions. The material got all over their skin, drinking water, lungs, and even in their eyes, along with coating all solid surfaces. And then we were surprised to see people from the neighboring islet arrive at the shore. They set out to hunt for birds and saw the explosion while they were out hunting and got very thirsty. They were very thirsty, and then they came to where we were staying in search of drinking water, and I believe I heard them talking about the color of the water changing. They said, the water color has changed. And you know it was in the 50s, and I'm not sure if they understood the word color, but they were saying, it's purple, it's violet, it's violet. This phrase, it's violet. And I did not know if it was really violet, but the elderly men said, the water is violet, it has changed. And so we gave them the water. Even though the color of the water had changed, they drank it because of their thirst. After seeing all of this, the islanders had presumed World War II had started again, and that the Japanese forces were coming back to kill them. They hopped into their boats and sailed to the smaller islets. As we wandered around, some of us started feeling dizzy and felt the powder in our eyes burning as if we had stared at the sun for a long time. And we kept asking ourselves, why do we feel sick? We were well before. For us, we'd go on and they would say, everyone needs to collect fallen coconuts. We will work together and see what happens next. Because we were assuming combatants would come and take us or kill us. We were surprised to hear people say, there's a ship in our lagoon. When the ship actually arrived, it was an American ship. Well, everyone hid in the brush because we were assuming that they were coming to kill us. So we went to hide. While we were hiding, they shouted at us, saying that everyone needed to go to the lagoon shore and get ready to board the ship because the ship came to pick us up. Another woman and I, her name was Kajin from the Genwood, were still hiding in the brush. We were the very last to come out of the brush because we were so scared to go. When we went there, everyone else was already on the boat. And you know the grilled chicken? They brought some out so we could eat. They threw overboard the food we collected for my grandparents. They said, you are not allowed to take anything with you except your clothes. And then we boarded. And even now I can remember when we were on the ship. I can still recall while they were shipping the boats while we were watching. Throwing us soap. They forced us to take a shower and then took us and lined us up next to the railing. They commanded, stop there and take off your clothes and throw them into the sea. They then gave us small white towels, and it was the first time anyone had worn a towel. The islanders were given the same rations as the soldiers. The Marshallese went through the regular mess line for meals and had the same ration as the crew. The meat course was the least popular. The majority of the party asked for more soup, bread, and vegetables. Hot soup was most in demand. Ice cream was the natural favorite of all the children. They were relocated to Kwajalein, ordered to bathe in the lagoon every day, as well as making them stay in a fenced area. 18 of the islanders complained of itching or burning of the eyes. It was estimated that the islanders were exposed to 130 Roentgen of radiation, which, while not immediately life-threatening, can cause nausea and skin reddening, and is well above safe limits. For perspective, the U.S. Atomic Energy Commission sets a yearly dose limit of 5 Roentgen to all workers. Over the next week, the islanders' conditions deteriorated. They had skin lesions, lost hair, and worse, beta burns, a kind of 3D sunburn that affected any skin that came into contact with the contaminated material, including the lungs and eyes. To add insult to injury, there was a cold epidemic that swept through the camp, causing even more to become ill. By early April, the radiation poisoning had worn off, and thankfully, no one had died. The Americans recognized that, quote, restoration to pre-evacuation standards is the inescapable moral responsibility, and began to repair and restore the islands. 10 surveys and radiological samplings were made at Rongelap Atoll. By the summer of 1957, the islanders were allowed to resettle back at their islands. But the test would soon come back to haunt them. A small Japanese fishing boat sat still in the ocean. It was dark inside the cabin as the crew slept while the waves slowly rocked the small vessel. In the previous month, nearly half of their fishing lines had been lost to a coral reef. Not wanting to come back from the voyage empty-handed, they pressed on. And even with engine troubles and a new inexperienced captain, they had had a good catch since then. They'd been out at sea since January and did not know that the U.S. government had set up a restricted zone around the island. And they had sailed just outside it, only 100 miles from Bikini Atoll. The crew jumped to their feet and ran outside. They were met with a spectacular sight. the weather changed drastically. It started raining, slowly at first, but soon grew in ferocity. But not normal rain. This rainwater was not clear, but instead white. Soon the wind began to pick up as well, dousing everything in contaminated water. It covered their catch of tuna, turning their normally blue fish gray. It stuck to their skin, hair, got in their eyes, and even throats. The white particles penetrated mercilessly. Eyes, nose, ears, mouth. It turned the heads of those wearing headbands white. We had no sense that it was dangerous. It wasn't hot, it had no odor. I took a lick. It was gritty, but had no taste. We had turned into the wind to pull in the lines, so a lot got down our necks and into our underwear, and into our eyes. And it prickled and stung. Rubbing our inflamed eyes, we kept at our tough task. This rain fell for 5 hours. In this time, the fishermen continued to perform their duties pulling in the fish. But something strange began to happen. They began to fall ill. First, they saw beta burns begin to form on their skin. Then it went downhill quickly. The crew had started coming down with dizziness, fevers, vomiting, as all of them were suffering from radiation poisoning. The 2-week voyage back from Yaizu was torturous for the crew. When they got back to their home port, the boat was so radioactive, Geiger counters detected elevated levels of radiation from 100 feet away. The boat was towed into a remote section of the port and put under armed guard. Unfortunately, the catch had already been offloaded and introduced into the fish market. A frantic effort to find and destroy these heavily radioactive fish was underway, and a panic enveloped the Japanese nation. Overnight, the fish markets could barely sell anything. It caused a decent economic blow to the country. But even with this frantic search to stop the highly radioactive tuna from getting out, at least 2 were sold and possibly eaten. The fishermen were not doing well either. They had promptly been sent to hospital outside the city for treatment. They were in hospital for months. And unfortunately, radio operator Akichi Kuboyama died from a secondary infection caused by his radiation exposure, leaving behind a wife and 3 daughters. For those who survived, it was torture. One survivor recounts, "My skin turned black and the skin started peeling and blistering. I kept getting sicker and weaker. I thought I was gonna die." To say that these events pissed off the Japanese public was an understatement. They were furious. Japan had already survived 2 nuclear bombs, and for even more of their citizens to have died, definitely hit a sore spot. The Japanese and American governments fought over compensation, and after a tense debate, each survivor was awarded 2 million yen, equivalent to $60,000 in 2024. But the torture was not over for the survivors. Besides the permanent medical damage, they were also socially ostracized. Their friends and family would avoid them, thinking that the radiation would spread to them. So many of the fishermen refused to talk and hid their traumatic experiences. Fishermen's families in the city had to pawn their clothes to live. They were also not given hibakushu status, unlike those who survived Hiroshima and Nagasaki. There was more international backlash, though. Manhattan Project scientist and Dr. Sir Joseph Roblat, who left the project after realizing the bomb wouldn't be dropped on Germany, deduced from fallout measurements that the bomb was much more dirty than the Americans publicly stated, publishing these results along with a slightly mistaken attempt at deducing the bomb's design, at which time the Americans could neither confirm nor deny, further embarrassing the American government. There's also the international effort to measure fallout from the blast. Using gummed film stations, the fallout that did not fall in the general vicinity of the test would circle over the Earth and gently fall over the tropical latitudes. All of this led to the US having to release a lot of information about the test that they didn't want to. Before now, nuclear testing was either seen as a faraway occurrence or as a novelty. Now, it was seen as a threat. One of the strangest results of this test was that it helped to spawn one of the most popular monster franchises in history, Godzilla. Director Ishiro Honda majorly changed the film to what it is now after hearing of the plight of the fishermen, and the opening scene of the film is directly inspired. It also helped to spawn the modern-day environmentalism movement. Before many of the scientists in this movement fought against acid rain or CO2 pollution, they were fighting against nuclear pollution. And Castle Bravo was a stepping stone for the movement and their participants, many of whom wouldn't have joined without hearing of the dangers of nuclear fallout. But we have forgotten about some people, the Marshall Islanders. After recovering from their initial bout of radiation poisoning, their journey wasn't over. Their experiences would haunt them to this day. At that time, you will try to weave yourself a sail, but there will be no plants. When you decide to build a canoe, there will be no trees. These are the things that you really need to think about now. For we are children of God, and we believe in the idea that the reason why we are safe today is that He has cared for us. God is really happy to help those who can help themselves. All of this was created by His might, and anything we do is likely to destroy His kingdom, meaning His plans will be subverted, and you need to be a leader who values safeguarding them. Protect your world, and protect the worlds around you. Thank you.